Is the comic artist Jeff, or?
No, although we could. We could definitely try that, but he's much better.
Oh. Hey guys, I'm David from Facebook. Our team, we've been coming here for a couple of years, but we run Gluster at Facebook amongst some other storage platforms as well. Oh, right. Sorry. Okay. So this talk is mostly about metrics, but in order to do that, our idea for giving this talk is just to give everyone a view of how we look at metrics, what we want in our metrics, and kind of where that plays into our model. So it's a little bit broader. It's and some of it will be a little bit redundant. How do web scale companies do this kind of thing? But I thought it would be a good background for everyone. So first things first, at web scale, which is something that companies like ours will implement with large distributed systems, but also can be done off the shelf with open source products such as Graphite. What we generally do is we have a bunch of hosts, hundreds, thousands, something like that. And we will collect data on each host with some kind of agent. Then we'll use a transport system. Maybe this is something like Thrift or some RPC, or maybe it's some kind of data bus. And we will transport metrics to some kind of central location. Maybe that's distributed, but it's a much smaller set of machines. At that central location, we'll aggregate metrics. And then this system will be the source of truth for monitoring. And to that system, we'll be able to interact with and write detectors against that system. So maybe we'll have some interactive graphs where we can drill down and look at data series. And I have some screenshots of a similar system to this. And then finally, you can query this central system. So we can write automated detectors against the data once it's there. So that's kind of the world that we're in when we talk about metrics. Similarly, it's probably helpful to talk about what we do with this data and how we identify issues in production. So we have alarms that query a system like I just mentioned. We look at request latency. We look at error rates. And we look at space usage. Those are things that are, if those are problematic, then our customers are having problems. And then finally, which is kind of the reason why we do talks like this, is sometimes we find out from our customers, which means we didn't have the right metrics. We didn't have the right alarms. Our customers do have their own metrics, which are helpful. But especially in an environment where you're perhaps selling a storage product to other customers, you don't have access to their metrics. So it's best for the storage system to know as much as possible. Once we have data in the system, we can analyze it and determine what's going on. So we take all of our log data and we put it in a central location. We have a tailing system for that for Gluster. We also make use of the IO stats translator, which I'll talk about more in these following slides. And these are implemented by some changes in Gluster. So the bulk of the talk is about metrics. So I'm going to go through what we talk about today, what we look at today, what we're working on this year, and what we would love to see in the future. So today we have two major metrics we look at. This is how we run a stable system. We look at what we call Sla Unweighted Average. This is the average latency of all FOPs coming into Gluster, and they're averaged together. We pick a certain amount of these FOPs which we consider to be important. We average them together and we graph that. This is a bulk metric. Secondly, we look at error rate. So similarly, we export how many operations issued an error. We have classifiers. What is an error? What is a hard error? For example, EROFS, that's not a good error to send your customer. But there are other errors that are okay, like E again. So these are our two top lines. Below the top lines, we build, all the other metrics are kind of either funneling into this metric or they're used to debug it once we look at this. So we start right at the system level, at the Linux level. We'll look at system load, we'll look at network I/O. Those are both very key indicators. This isn't Gluster specific, but I'm kind of painting the picture of how we get to Gluster specific metrics. This is a graph of host traffic. It turns out if you just look at what's going on the network switch, or you aggregate all of the I/O from each network device inside the tier, you will get a nice graph. This one is on a This is a graph that's running a test load, so that's why there's oscillations. You can also look at the load average. So this is across all of the nodes in the tier. This could be 20 nodes, let's say, but we also might want to break it up and look at individual nodes like this. So this is a well-balanced tier. If we had outliers, then we would be drilling down in. Then we look at disk stats. So there's a lot of information out of the block layer. So this is the thing that you would see on IO stat. So we'll look at things like A weight, we'll look at the queue depth. The IO sizes are important, which we can get in another place, and the bulk number of read writes a second. It's worth pointing out here that there's something called percent utilization. We don't use that. That is a kind of a flawed metric. Well, then you look at capacity of the file system. Simple, but could indicate issues with fragmentation or problems finding allocation. And then the overall IO operations per second on the disk. The next thing we look at is the system's view of Gluster. So this is the process scheduler has some ideas of what's going on. So I will show you a graph for this, but we will look at CPU percentage in memory of the management daemon, the brick daemons, and the protocol daemons. And we'll look at these independently. So for example, here's a graph of the brick daemons. And you can actually see here that there are some outliers at the top. It just so turns out that the top grouping of 3 lines here, those guys are on the same subvolume. So perhaps this graph is telling us that there is a hot file, or there is a slow subvolume, or something that's shared amongst that AFR children group. So next in line is kind of where the real meat is inside Gluster, is from IO stats. So this is from patches we've put upstream, but basically the IO stats translator is outputting important metrics to our system. So there's a piece in Gluster, which is open source, and there's a piece that's running on our systems, which is basically just scripting or a slightly more built out service to send things to our central system. So we're looking here at mean and top latency. This is broken down per op type. So we have writes, reads, and all the rest of the 30 or so operations. This is the part where we get our aggregated, or what we call unweighted operations average. And so that's the key SLA. Before we had this, I think it was about 2 or 3 years ago, we had no idea what was going on in the system. So if you or your customers don't have this aggregation, I might say they don't know what's going on in the system. So this is our top line SLA. So here is a graph of what this might look like. This is NFSD, and so what's cool about this is because it's in the IO stats translator, we will get this out of each daemon. So there'll be brick daemon stats, so that'll be there's only a few translators below that. It'll also be on the NFS, or the GNFS daemon, so we have more translators on top of that. And then in the GF proxy world, which I'm not showing here, you'll also get up the stack, so everywhere IO stats is. So here, this is something we might actually look at. This purple line, I believe, is unlinks. Unlinks are slow. Without DHT2, this kind of thing is going to go to every brick in the system. So, in systems like ours, we might have 30 or more of those. The orange line here, that is lookups. So lookups are heavy on the metadata on the backing file system, like XFS or Btrfs, and they're slow. So once we have that, that's our time series look from IO stats. We also have sampling from IO stats. So again, patches and IO stats. What we do is we dump sample data, so actual FOPs, into a file for ingestion. And there is a sampling rate. This is an example of a rate that we would have set as a Gluster volume level. And what this looks like, I'll just show, this is text here, but because I can't really show you our bulk aggregation system, we'll output something like this. So the file will have, create stats, statfs. It will have latencies. It will have where did it come from. We'll get path names, which is another set of patches that we did. This goes into a bulk data analysis system. So this could be any kind of database on the back end, like MySQL, like Hive, something like this. And then there would be a query engine that you would need to look at this data. I know there's things out there in the open source. Ours is homegrown. What we can get from this, now that it's in a centralized data store, is we can get derived metrics and diagnostics. So if you make a patch to Gluster to try to get a new metric, like for example, let's say you don't want mean average latency, you want median. That would be a code change in Gluster. You'd have to push that out, roll it out, make sure that it works. That could take time. So we will do that kind of thing for our time series data, but it will be a long development cycle. If you're in this sampled thing, you can actually build those out in queries and find new metrics right away. They might be slower because it's a sampled full data set system, but it's much more flexible. So we'll actually prototype there, and we'll prototype alarms there. We'll also use this for debugging. So what are the clients doing? Is there like a particular bad client? Let's say we have 2,000 clients, and somebody's doing something that is not implemented well on like the POSIX edge case thing. We'll be able to find them, or hopefully, in this data set. And then finally, they'll capture outlier as well. So whenever you decimate data in some kind of average or something, you're going to lose something. A sampling will at least have some statistical chance of capturing an outlier, even if you won't get everyone. All right, so what are we doing now? This year, we worked on P90 and P95 data from IOStats. So this isn't available yet because we're still finishing it. But P95 and P99 are recognized as better indicators of badness, at least in groups like ours. What P99 is, it's in a latency perspective, it will be the latency and which all ops are falling under. And the reason why you look at that is because it tells you how bad is bad. So that would mean that 1% for P99, 1% of the operations are worse than that number. And this is good because it tells you how bad the bad IOs are. It also tells you how good the bulk of the IOs are. So we put this in IOStats. Next is Enfuser. So we have a talk on this, but this is our client. And one of the main reasons why we're doing Enfuser is so we can get metrics out of it. Since Enfuser is control, it's a user space system. We have control of it. We can get stats out of it. And it's much better to look at what's happening closer to the customer than it is to infer it from the server stats. So we kind of have a diagram. This is what we're doing now without Enfuser. So you have the NFS server, and we're getting metrics out of IOStats kind of right there under the server translator. We don't know what's going on with the kernel. There's problems with kernel NFS for sure. And we don't know what's happening with the user application. And we know users, they could have plenty of problems in their code. So if we can get closer to that, our metrics are going to be more reliable for understanding like customer empathy is what we'll call that. So third thing we're working on is per namespace stats. This is also related to another talk that we're giving on QoS. So as part of QoS, we have to tag the IOs to find out who's doing them. We would like to have per namespace stats. So let's say you have customer A. What is their latency? What are their create latencies? What's their create latencies in the bricks versus the NFS? We'll be able to get that with per namespace stats. And then finally, just a few comments on what we'd like to see in the future. So per translator metrics, something that's been talked about a while here, we would love to have those. There's a slightly different slant we might have on how this should be done. Facebook and groups like that to kind of build their services by making them simple. And so with per translator metrics, one idea is that every translator could implement a function which dumps out some stats, perhaps latency between the wind and unwind. And you could write that into a dictionary. And what we have now is IOStats has a gather thread which is currently dumping out these bulk stats that we only have per instance. If we could somehow gather them for each translator, dump out the stats, that would be enough. We would pump it into a shared time series graph or querying engine like showed you before, and we would be able to infer things just on that. So basically the idea is get the data and then figure out what you can do with it instead of building something perfect at first. And then secondly, accounting quotas are big for us. So there is a quota implementation in Gluster. It's pretty good in that it's consistent, and it's very good at tracking the exact quota so that users don't go over what they've been assigned. What it is not as good at is performance, and this is because of the consistency guarantees. So we would be interested in quota implementations that are looser. It's basically good for accounting, finding out what's going on, how fast are the quotas growing, are users just dumping data onto the system, and kind of who's doing it. At a place like Facebook, we have a little bit more control over who's doing what once we figure out what it is. So for us, faster, simpler, better. And that's it. That's all I got. Short talk. Do you guys have any questions?
So the per translator metrics feature is sort of already implemented in experimental branch. Have you checked that?
Yeah. I've heard of that. We haven't started using it yet, though.
Okay. No, of course, experimental is for just testing, for sure.
Yeah.
Okay.
Yeah. Thanks for bringing that up. That's important.
Yeah.
So you mentioned in the per translator FOPS again, per translator metrics, we were looking at wind, unwind, and latencies of that nature. Are you also interested in other stats at a translator level, like how much is, let's say it's a caching translator, what's the space used by the caching translator, what are the cache hits, what are the cache miss ratios, and things like that? Effectiveness of a translator.
I mean, off the cuff, yes. Yeah, I mean, you mentioned like how much memory would a translator be using, like how big are its structures? Yeah, probably. There's a lot that can be done here, but there's a trade-off, right? If you have a system that gives you every possible data output, it's going to be a little harder to design, and maybe it will have more bugs because it's more code. So we've found, and you can see because it's a simple presentation, what we do is we just get some metrics, dump it into a bulk system, and then we spend time looking at it. And there's actually a lot of signal in the data. You just get twice as many time series as you had before. There's tons of stuff to dig in there.
Other questions? Okay, fine.
What do you use Gluster for in Facebook?
Well, we try to store data, and then we try not to lose that data once it's been stored on our systems. We use it. I mean, I can't speak to everything, but two things that it are particularly good at. We'll say that it's good at storing backups, which is not as interesting. It's also very good at utility storage. So Gluster is easy to set up, especially when you have automation around it. We can deploy it in perhaps smaller increments than other storage systems that are very, very large at Facebook. We do use it in a fairly narrow case in that we only use some translators. We only use NFS. But yeah, that's about as much as I can say, at least publicly.
Nothing else? All right, thank you so much.